Good evening, everyone, and welcome to Straight Science. Straight Science is an evening science presentation series put on by UAF, Alaska Sea Grant here in Nome, and UAF, University of Alaska Fairbanks, Northwest Campus, also in Nome. And UAF Campus and UAF Alaska Sea Grant, we are public servants of the Bering Strait region. We serve all peoples of the Bering Strait region, which includes the Inupiaq, Yupik, and St. Lawrence Island Yupik peoples. So tonight, if you had just joined, you would have heard Evie talking about her first trip to Nome aboard the Healy, the U.S. Coast Guard icebreaker Healy. Hi, Orland. Hey, Orland, back here in the hub of Nome, we seem to be having a little trouble with our Starlink. We've kind of blacked out at once. So if you could just keep the video off, that would be awesome. But we're so glad you're on. Thank you so much. Awesome. So Evie was on the U.S. Coast Guard icebreaker Healy, first time getting ready for her first research, and she said she came to a Straight Science, so she is not unknown to Nome or Straight Science. And as time progresses, so has Evie. She's now a speaker. She is a PhD candidate, and after you see this presentation, you'll just give her her PhD because it's going to be beautiful to look at, and she's very, very smart. Honestly, she's world class. She is a PhD candidate at the Woods Hole Oceanographic Institute, and her research focuses on harmful algal blooms in the Pacific Arctic. So what she has to say will be important to us all. And she's part of a larger, the larger issue of what's going on in the Bering Strait region with climate as our oceans are warming. This is a very serious issue to the region and something we all need to get caught up to speed fairly quickly. So with that, Evie Fachon, we're so glad you're here. Take it away. And questions will be held until the end for everybody. So thank you so much. Take it away, Evie.
Awesome. Thank you for the intro. Thanks for the opportunity to speak today to folks in your region. So once again, I'm Evie Fachon. I'm a graduate student in Don Anderson's lab at the Woods Hole Oceanographic Institution, and I'm studying harmful algal blooms in the Pacific Arctic for my graduate thesis work. So today I'm going to be giving an update on the Bering Strait and Chukchi Sea harmful algal bloom research that we've been doing. To start, we're going to give an overview of the toxic algae, Alexandrium, that we study and the illness that it causes, paralytic shellfish poisoning. We'll also go into what we already know about bloom dynamics of the species in the Pacific Arctic. And then we'll go back to summer 2022, last year, when we saw a really large bloom of Alexandrium in the Bering Strait. At the time, I was on a research vessel in the region collecting observations in the field, and we were able to share some of those observations in real time. But we also collected many different samples and data that we brought back to work on in the lab. And over the past year, we have a lot of new results and analysis from that bloom that we can share today. And then finally, I'll talk a little bit about what we're doing now this year in 2023. But before I get into all that, I just wanted to talk a little bit about where I'm calling in from. So I work at the Woods Hole Oceanographic Institution that's located nearly 4,000 miles away, all the way in Cape Cod, Massachusetts. It's 10:30 here on the East Coast, so this is definitely winning the award for the latest talk that I've given yet in my career, but that doesn't matter. I'm really happy to be here and talking no matter what time it is. Whoops. There we go. All right, so this is our campus here in Woods Hole, or we call it WHOI for short because Woods Hole Oceanographic is kind of a mouthful. And people here study everything from life at the deep sea vents to how currents move through oceans around the world to water chemistry at coral reefs or on really large scales. And we also, in our lab here on the 3rd floor of the Redfield building, study harmful algal blooms. So HAB or HAB stands for harmful algal bloom. You might have heard these referred to sometimes as red tides, but we really try to use the term harmful algal bloom instead because not everything that changes the color of the water is actually a harmful bloom. So we can see an example of that in this image on the left. This is taken by a plane flying over Kachemak Bay. they looked down and saw that the water was really bright red, got worried that something was going on, and got someone to go out and collect some samples. When they brought those back to the lab, they found out that it was an organism called Mesodinium, which is this beautiful bright red color, but actually isn't harmful, and the bloom itself disappeared within a day with no ill effects. On the flip side, there can be blooms that might not change the color of the water at all, but can still be really harmful or toxic. So on the right here, I have a photo from the Bering Strait this past summer. And we know that at the time we took this image, there was a really toxic bloom occurring. But from our position on the ship, just looking out over the water, it looked pretty normal, kind of gray or blue, not like anything crazy was going on. So that's why we call it a HAB. In Woods Hole, we actually have 2 different HAB labs that work together to do research in Alaska and also in many other places in the US and in the world. So before I dive into our research and results, I just wanted to show you some of these faces because all of these folks contributed to the research that I have the opportunity to share today. Don Anderson is my advisor. Other folks in his lab include Mindy Richland, Kaylee Horn, Nate Spada, and Anishka. And all of these people have either come to Alaska in person to help do this research, or they work on the data that we bring back with us to Woods Hole. Mike Brosnahan is another scientist who also studies harmful algal blooms, and he uses robots and automated platforms to do most of his research. His technician is Maroon Pathare, and she might be a familiar face because she's actually come to Nome several different times to set up instruments that go out on research vessels. So you're probably wondering, why is this group of people coming all the way from Woods Hole to do research in Alaska? And that's a really good question. So the reason is that every year we actually have our own really big algal blooms right here in New England in the Gulf of Maine. My advisor, Don, has spent his entire career understanding the biology and the ecology of these blooms and collecting data which helps predict and mitigate their impacts here in New England. On this slide, I have 2 headlines, both from this past summer. The one on the top might look familiar. It's from the Nome Nugget, an article by Deanna, which was entitled, "Researchers Find High Concentrations of Harmful Algae in Regional Waters." 1 month earlier, we had this headline in New England: "Toxic red tide bans shellfishing across Massachusetts North Shore, making clams and oysters dangerous or fatal to eat." So these were 2 different events happening on completely opposite sides of the country, but the species that was causing it is actually the exact same thing. The culprit, if this video will work, great, is Alexandrium catenella. So here I have a video showing what these cells look like at different magnifications. You can see these little golden balls tumbling around in ones or in pairs. They're part of a group of algae called dinoflagellates, which means that they use this little whip-like tail called a flagella to actually swim and move around in the water. Seen up close, I think they actually look kind of cute, especially if you're a nerdy biologist like me. But when you have large accumulations of this algae, they can cause some really, really serious problems. This is because Alexandrium produce a potent suite of toxins called paralytic shellfish toxins. And these accumulate in organisms that eat Alexandrium and are passed on through the food web, as you can see in this figure on the right. Toxins can accumulate to particularly high levels in shellfish or crustaceans. And in a lot of parts of the world, this is one of the big concerns as it relates to these blooms. So for example, here in New England, we have commercial and recreational shell fisheries, as well as aquaculture operations. And all of these may need to shut down in the event that an Alexandrium bloom occurs. However, zooplankton and small fish can also accumulate these paralytic shellfish toxins and pass them on to marine birds, mammals, large fish. And any of these could potentially pass toxins on to humans that consume those contaminated seafoods. As I'm sure you already know, these blooms have many different serious impacts. They're harmful to wildlife and ecosystem health, causing die-offs of marine birds, mammals, or fish. They're a very serious public health risk. These toxins can make people very, very sick. Symptoms of paralytic shellfish poisoning include numbness, usually starting in the lips, or tingling, nausea, paralysis, which can start at the extremities and eventually move on to the respiratory system. In extreme cases, this can actually stop someone from breathing and be fatal. There's no antidote or medicine that can clear the toxin from your system. So people who are affected need to get to a hospital as quickly as possible, where they can be kept on life support until that toxin passes through their body. These blooms are also expensive. Shutting down a fishery or an aquaculture operation can be a huge loss in revenue, both for the fishermen, but also for restaurants and other industries that depend on that seafood. And in a place like the Bering Strait, where subsistence is a way of life, having to forgo something you might harvest can mean going to the grocery store and spending more money there, which I'm sure I don't have to tell you can add up really quickly. Alexandrium has a complex multi-stage life cycle with some really useful and kind of clever strategies that actually help it survive. In the winter, when it's cold and dark and just not a good time to be a plankton swimming around in the water, they survive down in the sediments as a dormant cyst. These cysts just sit there, inactive, waiting for temperatures to be warm enough for them to germinate. And germination is the term we use to refer to when these cysts release these swimming cells that come up into the water and begin to grow and divide and form these big blooms. As the bloom begins to end, they go into the sexual part of their life cycle and form these little cells called gametes. These gametes find each other and pair up and fuse to form what we call a planozygote. And eventually that planozygote will settle down as a cyst and the cycle can repeat. So this might happen the following spring or summer, but if it's not warm enough, those cysts will stay down there in the sediment, waiting for the temperatures that they need to start a new bloom. One study has reported that cysts can remain in the mud for over 100 years and still be able to germinate and form these swimming cells. So in the Gulf of Maine, we have blooms of Alexandrium pretty much every year. There's a large accumulation of these dormant cysts in the sediments of the Gulf of Maine that release those swimming cells every spring. Researchers will use this cyst distribution along with environmental information such as temperature, nutrients, and day length to actually make models of these blooms. So in the center video here, we have a model of a bloom in 2005. You can see those cells starting near the coast, getting mixed into waters offshore and down south, and becoming really, really dense, eventually reaching all the way down underneath Cape Cod before eventually dissipating in the month of July. 2005 was actually a really bad year for New England, and we had to have fisheries closures all the way from the border with Canada down to the islands below Woods Hole. So right here, we have just one example of how these cysts in the sediment can form these big toxic blooms, which ultimately have human and environmental impacts. Oops. There we go. So as many of you probably already know, these algal toxins are now being detected in the Alaskan Arctic. There's already a long history of paralytic shellfish toxins down in the Gulf of Alaska, but in the Bering Sea and northwards, this is really more of an emerging issue with only some sporadic historical accounts. This map is from Kathy LaFay's 2016 paper, which showed that marine mammals from all around the Alaskan coast up to Oceanographic are testing positive for these algal toxins. And similar results have also been seen in seabirds. In 2013, a Japanese research group reported high concentrations of Alexandrium cysts in the sediments of the Chukchi Shelf. This map on the left shows those results with this really large circle indicating where they saw the highest cyst concentrations. These results motivated our team to start working in the region, and between several research cruises in 2018 and 2019, we were able to collect many sediment samples from around the region and map this huge accumulation of Alexandrium cysts on the Chukchi Shelf. I've also plotted the Gulf of Maine cyst bed here in the inset to the same scale, so you can see how large that Chukchi Sea cyst bed is compared to what we have in the Gulf of Maine. But this seed bed on its own is by no means small, and as I just showed you, it's enough to cause blooms in New England every year. The Chukchi bed is both much larger and much denser than what we have over here in the east. As I began to mention, the germination of these cysts is temperature dependent. So this plot on the left shows how long it takes a cyst to germinate under different temperatures. We have days until germination on this y-axis and temperature on the x-axis. And so you can see, for example, that at 2 degrees Celsius, it takes around 42 days for a cyst to germinate, so well over a month. At 4 degrees, it takes more like 21 days, so almost half that time. And at 8 degrees, it takes only 10 days or so for cysts to germinate. So you can really see that as bottom temperatures warm, these cells can germinate more and more quickly and get that bloom started. In recent decades, we've seen that the bottom temperatures on the Chukchi Shelf in the location of that cyst bed are indeed getting warmer. And most recently, they were well up over 6 degrees, so more than sufficient to get these cysts going. So given those warming bottom temperatures, it's unsurprising that we've started to see blooms in the Bering Strait and on the Chukchi Shelf. These maps show some examples of blooms from past years, starting with this one detected by the same group that first reported those cysts up on the Chukchi Shelf. They saw a bloom in the Bering Strait in 2013. In 2018, we saw a bloom in the location of that big cyst bed. And in 2019, we saw another bloom further south in the Bering Strait. Across all of these years, the cell concentrations were moderate, with the highest density of Alexandrium being around 8,000 cells per liter. So from all these observations, we've developed a conceptual model for how blooms can occur in the Chukchi Sea. Blooms can be carried or advected on currents through the Bering Strait, where they then deposit their cysts on the shelf as those currents slow down. The Bering Strait acts as a funnel through which water from many different sources passes. So a bloom that we see in the strait could potentially come from Alaskan coastal waters, it could come from the Gulf of Anadyr, or it could originate more centrally somewhere in the Bering Sea. Once those cysts are deposited on the shelf, they could remain there for many years if conditions are cool. However, in recent years, under those warming bottom temperature conditions, it's increasingly likely that those cysts in the Chukchi will be able to germinate and start their own northern blooms. So this diagram shows both of those processes, both the advection by currents and that cyst deposition on the shelf, as well as the formation of a local bloom under warmer conditions. In order to better understand some of these dynamics, we planned a harmful algal bloom focused cruise for the summer of 2022. Bob Picard, pictured here, was the chief scientist on that cruise. He's also a researcher at Woods Hole. He's given many a straight science talk in the past. He's a physical oceanographer, and we actually work really closely with him to understand how blooms are shaped by currents, by winds, and other environmental factors. This ended up being a two-part cruise, and both of those legs departed from and returned to Nome. The coverage of each part is shown in these maps on the left. And you can see that we were able to visit locations in the northern Bering Sea, in the Bering Strait, Chukchi Shelf, and all the way over to the western edge of the Beaufort. These all took place aboard the Norseman II. So this is a photo of the science party from that first leg. Maybe you recognize some of these folks because we were wandering around the streets of Nome last summer. But all these people worked really hard to collect some of the data that I'm about to show. So we collected many different measurements on that cruise. We had plankton tows, we took water samples to look for Alexandrium, but also other HAB species. We collected sediment cores to look at the vertical distribution of cysts through the mud, as well as grabs that we used to look at surface sediments, and also collect clams, worms, and other invertebrates to test them for algal toxins. But today, just to start, I'm going to focus on data from the Imaging Flow Cytobot, or IFCB. This is a neat video of the IFCB. It's a high-speed robotic microscope. It was originally invented at Hui by the SOSIC lab, and now it's commercially available from a company here on Cape Cod. But the way that it works is it pulls up a water sample, it runs it through in a very thin stream past a laser. That laser can detect fluorescence from the algae, or it can detect particle scatter. And every time it detects something, it triggers a camera to take an image. The way you're seeing it in this video is kind of slow compared to how it happens in reality. This instrument can take thousands of images per sample, can collect one sample every 20 minutes or so. And so it processes these extremely, extremely quickly. Once we have those images, we run them through a machine learning model, which looks at the shape and the size of that picture, and then gives us an identification and a confidence of how sure it is that it picked the right ID. We got this. There we go. All right. So on the Norseman, we had an IFCB configured to sample from an underway seawater line aboard the vessel, so it could actually produce imagery of phytoplankton as the ship moved along its cruise track. And this allowed us to detect those harmful algal cells in real time and to respond and to adjust our sampling plan accordingly. Based on our past observations in the region and what we know about the toxicity of Alexandrium, we decided before the cruise to define bloom concentrations as anything greater than 1,000 cells per liter. And this threshold is also consistent with blooms and toxicity that we've seen in Southeast Alaska, as well as in the Gulf of Maine. So this wasn't supposed to be a monitoring cruise. We're researchers, ecologists, biologists, but of course, since we're studying something that's so related to ecosystem and human health, it's definitely our responsibility to make sure that coastal communities are made aware if we see something in their waters that they need to know about. So prior to the cruise, we were lucky enough to connect with Gay and Emma Pate and Orange Sound Health Corporation and Alaska Sea Grant, and to let them know that we were going out and what we were looking for. And in the event that a bloom was detected, we would get in touch with them and work together to create some sort of risk advisory text that could then be passed on to communities. And we put this plan into action extremely rapidly. Only several days out of Nome on July 25th, so almost a year ago today, practically, we detected concentrations of over 20,000 cells per liter just west of St. Lawrence Island near Gamble. And so here on the left, you can see what that looked like in our imagery. All these little round balls are Alexandrium mixed in with some other phytoplankton species. And on the right, you can see the distribution of those initial observations. Each point is an IFCB sample. The color represents how dense the cells were in that place. We also have those blue arrows, which represent the current as measured by a shipboard instrument. So we could see not only where the cells were, but also where the water was moving at that time. Over the course of the next month, the bloom progressed through the Bering Strait and it intensified, reaching concentrations of over 150,000 cells per liter. So this is really, really dense for an offshore bloom of Alexandrium. On the right here, you can see a moving map of this progression based on the IFCB observations in the ship track. So we first saw it down here near St. Lawrence. It started to move up through the strait, and winds also mixed it east into Kotzebue Sound and into the Alaskan coastal current. As it was mixed east, it got even denser, reaching those really, really high concentrations by mid-August. And then by September, the last time we observed the bloom, it had fully passed through the strait and was starting to decrease in intensity. We can also look at this from another perspective. So in addition to those surface samples that the IFCB was collecting, we also collected water samples from across different depths, so we could look at how that bloom was distributed throughout the water column. Here I'm showing just one of those sections that we did. This is the section in the very middle of the Bering Strait, stretching from just offshore of Diomede to just offshore of Wales. And in each of these panels, we're looking at a slice of the water. We've got depth on the y-axis and distance across from Diomede to Wales, or close enough on that x-axis. The color in the background is the temperature of the water that we measured at the time. And then each of these colored points is one water sample that we took and counted for Alexandrium. So the first time we visited this line on July 28th, we could see that the cells were on the western side of that transect and were mainly at the surface of the water in concentrations of around 2,000 to 5,000 cells per liter at the surface. When we returned several weeks later on August 18th, that bloom stretched all the way across the strait from side to side and was at its densest concentrations of over 100,000 cells per liter. And it wasn't just dense at the surface. We could see that there were over 5,000 or 10,000 cells per liter down to 20 meters of depth. So you have about 60 feet there at the surface, just full of this bloom. When we returned again on September 5th, the bloom had almost completely passed through the strait. There were very few cells left at any of the depths that we looked at. So this was a really extraordinary event. It made regional news, and your local media, the Nome Nugget and KNOM, did an incredible job reporting about this bloom, both during and after the event. And I know folks like Gay and Emma were incredibly busy spreading the word, making sure that health clinics were prepared to recognize and respond to the symptoms of paralytic shellfish poisoning, and collecting water and seafood samples for additional testing. As you might already know, one of the clams that a family submitted for testing came back as being over 5 times the regulatory limit for saxitoxin. So this is a sample that could have made someone very, very ill if it was eaten. One near miss that we can point to from this event. During and after the bloom, we were asked many times, like, how toxic are these cells? How bad is this bloom? And unfortunately, that wasn't something we could answer quickly, just because analyzing those toxins means bringing a water sample back to the lab and running it through a multi-step process to measure actually many different kinds of toxins it might contain. Before I get into those results, I just wanted to kind of give a quick primer on the paralytic shellfish toxins that Alexandrium can produce. So it doesn't just produce a single toxin. There are actually many different forms that all differ slightly in their molecular form that the species can make. And to compare them all, we use something called a toxin equivalency factor, which basically helps us take all these different toxin forms and put them on the same playing field so we can figure out how intense or how potent a strain of Alexandrium is. At the top, we have this red one. It's called saxitoxin. That's the most toxic molecule that this organism can produce. It can also make something like neosaxitoxin, which is also fairly potent, around 92% as bad as saxitoxin. And then all the way down at the bottom, we have things like the C toxins, which can be maybe 1% as strong as saxitoxin. So it really, really matters which forms of these toxin a bloom is producing. And that will tell you a lot about how much toxin can accumulate throughout the rest of the ecosystem. You could have a really low density bloom of something producing lots of saxitoxin that might actually be worse than a super high density bloom of something producing something really lowly toxic like C toxin. So this is the average toxin profile from the Bering Strait bloom. You can see that we have a really high proportion of this orange color, that's goniotoxins 1 and 4, so that's one of the more potent forms. We also have a lot of that neosaxitoxin and saxitoxin, as well as some goniotoxin 2 and 3. So looking at this all together, we can see that this was some very potent cells that were present throughout the bloom. We collected many different samples, starting when we first saw the bloom near St. Lawrence and extending all the way to the end as the bloom passed through the strait. And throughout all these samples, we saw that this toxin profile remained very, very consistent. It was pretty much the same at the beginning as it was at the end. Interestingly, we actually had the opportunity to sample another bloom in the Bering Strait back in 2019. And during that bloom, we saw a very similar toxin profile in the few samples that we collected. Again, lots of this orange, goniotoxins 1 and 4, as well as this yellow, red, and green. So we're going to dig into this more and see if we can find out more about where these blooms came from and maybe why they were so similar to each other. We can also look at what kind of water the bloom was found in. So here I've got temperature plotted on the y-axis and salinity on the x-axis. And each of these points represents a single IFCB sample taken over the course of the cruise. And once again, color is the density of Alexandrium in that sample. So there's a lot going on here, but we can kind of pare it down to look at only samples that contained at least some algae, or samples that had more than 1,000 cells per liter, or samples that had more than 20,000 cells per liter. And so when we do this, this concentrated patch emerges, and we can see that those densest bloom concentrations were from 30 to 31.5 PSU of salinity and from around 5 to 9 degrees Celsius. And we're going to continue to work with Bob Picard and his group more to see what else we can learn from these water signatures about the water mass where that bloom was found and where it potentially may have come from. We've also been digging more deeply into the IFCB imagery to see what else we can learn about that bloom and what it was doing. So I want to revisit this life cycle that I presented earlier. And each of these different cell stages that I talked about actually has a fairly distinct appearance if you know what you're looking for. So these vegetative cells, the ones that are dividing and growing and forming these blooms, are kind of medium sized. They show up by themselves or maybe in these little chain style pairs. As it moves into its sexual phase and produces these gametes, the cells get really, really small, or sometimes we can even catch them fusing together, and it kind of looks like this. Once they've fused, the cells start to get really big. They form these large planozygotes, and this is the stage right before you start to get new cysts. So we've seen some of these bloom dynamics play out in research in New England. These plots show the progression of an Alexandrium bloom in a marsh system just a short drive away from our lab here on Cape Cod. In this top graph, we have the density or the biovolume of Alexandrium in the environment. This plot below shows the cell size of shells throughout the bloom, with this dark line representing the average size of a single cell. This was over the course of a month from the end of March to the beginning of May. So we can see that as the bloom begins, we have these medium-sized cells. They're bouncing up and down a little bit as they go through their daily division cycles. And as they do this, that bloom is accumulating and reaching higher and higher densities. After that density peaks, we see that the cells suddenly become really small as these gametes start to form. And following that, they start to get really large as we see more planozygotes. And as these planozygotes appear, we actually see that the bloom itself disappears. And that's because these planozygotes are settling down, making new cysts, and that bloom is over. So looking back on some of the imagery that we collected this past summer, we can actually see evidence of something really similar going on. In this map on the left, I have plotted the average size of the Alexandrium cells during the last pass of the ship south through the Bering Strait and back towards Nome at the beginning of September. And as we passed down, we saw that the cell size changed pretty dramatically. We had lots of these small size cells, gametes up north, and then lots of these larger cells as the ship moves south. You can see some pictures here of kind of what that looks like in the imagery, as well as how that average size changed and grew over time as the ship traveled. So right here, we have evidence of that Bering Strait bloom forming some of these planozygotes, getting ready to drop new cysts just as that bloom began to end. So we wanted to see if this actually happened. Did that bloom deposit new cysts in the Chukchi Sea as it was ending? So we actually had this opportunity during an additional research cruise on the Sepuliak this fall. We were actually able to collect additional sediment samples from some of the locations that we'd already visited this past summer and to compare cyst densities between summer and fall. Here I'm showing you the DB03 section. This is a line that runs from Point Hope over to the edge of the border with Russia. There were 7 different locations on that line that we were able to hit in summer and fall. So I've plotted each of them here with the summer density in the light color and the fall density in the dark color. And so what should jump out at you right here is that there were many more cysts at almost all of these stations in summer relative to fall, indicative of the fact that this bloom deposited new cysts as it was ending. So when we think back to those conceptual mechanisms that I discussed earlier, it's clear that our 2022 event was one of those advected, current transported blooms. It started somewhere in the Bering Sea, it passed through the strait, and then it dropped those cysts onto the Chukchi Shelf. But what about that big cyst bed? Was anything going on up there? So this summer, bottom temperatures on the Chukchi Shelf were actually colder than compared to prior years. The map on the left shows the bottom temperatures that we measured during the cruise. You can see that in the region of that cyst bed, we've got temperatures of around 1 or 2, maybe 3 degrees Celsius. The map on the right shows the difference between what we saw this past summer and the average climatology from 1970 to 2020. So blue colors here mean that those locations were colder compared to prior years, and red would mean that they were warmer. But overall, you can see that in that cyst bed region, we did have pretty cold temperatures, at least for 2022. Once again, we can look at this from a different perspective. So here I've got those slices of the water column, this time for the Ledyard Bay transect, which runs right across that high density cyst hotspot. On the top, we have the transect or sample from 2019, which shows that there were very warm temperatures throughout the water column. And at the bottom, we have temperatures of 5, 6, 7 degrees Celsius. In 2022, it's a much different picture. All this blue is once again 1 to maybe 3 degrees, but definitely a colder year this past summer. So thinking back to that plot that I showed you really early on, we can see that under 2022 conditions, it would take well over a month for those cysts to get going. Whereas in 2018 or 2019, you're looking at a much shorter time frame of a week or like a little bit more. So based on all of this, and also the fact that while we were traveling on the Chukchi Shelf, the IFCB detected very few Alexandrium cells, we believe that that cyst bed was actually not active this past year. So once again, returning to that conceptual model, we had that infected bloom, but we did not have any germination happening from the northern cyst bed. One big lingering question from 2022, and one that I'm sorry I don't have the answer to yet, is where the heck did that bloom come from? We know that the Bering Strait represents this confluence of many different water masses, including Alaskan coastal water, Bering Sea water, and the Gulf of Anadyr. And we know that we first saw the bloom to the west of St. Lawrence, so it didn't start in Alaskan coastal waters. Instead, it came from somewhere in the Bering Sea. It may have come from the Gulf of Anadyr or somewhere more centrally located. We're still working with Bob Picard and with others to try and track back and figure out where that bloom may have started. We've recently finished analyzing all of our sediment data from 2022. So this is our updated cyst map. In addition to those Norseman cruises, we were also able to receive sediment samples from the Northern Bering Sea cruise and from the Southeastern Bering Sea cruise. And that really has expanded our sample coverage for this year. What should jump out at us right away is the fact that there's actually a very significant accumulation of cysts down in the Southeastern Bering Sea, near St. Paul, a little to the north, and also a little to the east. We can also see that that Chukchi cyst bed persists. It's still present up there, as well as a smaller accumulation of cysts over by Oceanographic. This southern cyst accumulation could serve as a source for blooms in the Bering Sea, but it's unclear at this time whether something that starts down here would be able to make it all the way up to this part of the Bering Strait by the end of July. There's clearly a lot more work that we need to do to understand the connectivity of this whole system, not to mention we need a lot more data about what's going on further to the west. So some takeaways from 2022. Having that IFCB aboard the ship led to real-time bloom detection, allowing us to see that bloom and respond to it in real time. As far as we know, this is a first not only for Alaska, but for anywhere for a time that an IFCB was used in this way, shipboard, to detect and alert about a HAB event. This was a massive and highly toxic bloom, which was unprecedented for the region, but these events are likely to happen more frequently as conditions warm. We know that the bloom originated in the Bering Sea. We're still not sure exactly where, but that it was mixed east into Alaskan coastal waters as it progressed. That event was an infected bloom, and it led to new cyst deposition on the Chukchi Shelf, but low temperatures on the shelf suppressed any germination from the northern cyst bed. So all of this begs the question, what about 2023? And so we actually don't have a harmful algal bloom crocus cruise for this summer. The one that happened last year was a one-time NSF-funded cruise. However, the Schooliac and the scientists that are using it for their funded programs this summer have all agreed to host one of our IFCBs aboard the vessel so that it can ride along and detect algal communities as the ship moves. Maroon here has traveled out to Seward and Nome to configure the instrument aboard the vessel, and it's currently collecting data up in the Chukchi Sea. And all of this work is being supported by NOAA's National Centers for Coastal and Ocean Science through the HAB Event Response Program. These are the 4 cruises that the IFCB will be deployed on this summer. The first one is the Chief Scientist Training Cruise that happened at the beginning of June and left from Seward and transited up to Nome. From there, we've moved into Kevin Arrigo's primary production in the Chukchi Sea interdisciplinary cruise, and they're currently working up off the Chukchi Shelf, monitoring ice algal and under ice blooms as the ice retreats. They'll be up there for a couple more weeks, but at the end of July, the ship will return to Nome for Sarah Fowles' Bering Sea coring cruise, where it'll work its way south, down through the Bering Sea into Dutch Harbor. From there, at the beginning of September and into October, we have the DBO Eco-Foci cruise led by Jackie Grebmeyer, Seth Danielson, and Katrina Eichen. And that cruise will leave from Dutch Harbor, work all the way up across to the North Slope, and then back down to Nome. So over the course of 4 months, the ship will be in and out of Nome 4 different times, providing multiple opportunities to capture snapshots of any bloom activity in the region. So if we see something, we're going to build upon our model from last year. The IFCB is aboard the ship collecting data. One huge difference is that we don't actually have a person aboard the vessel this summer. Instead, we have a remote connection to that IFCB, so we can actually log in from our desks here in Woods Hole and see how the instrument is working and make adjustments as needed. We'll look at those images, see if there's anything that people need to worry about. And if we see a harmful algal bloom, we'll get in touch with folks at Norton Sound Health Corporation and Alaska Sea Grant to draft advisory text that can be passed on to communities. One huge caveat to all of this is that we're really limited by where and when the ship travels. So we can see whatever's in the water where the ship is, but we really don't know anything about places or times beyond that limited sampling coverage. We've also been working to improve the image classification of our data. So after last year, we noticed that our image classifying model, the thing that sorts through all of our imagery and tells us what kind of plankton we have, was actually working pretty poorly for the Alexandrium and that big bloom. It was only correctly identifying around 50 to 20% of those cells. This classifier was initially developed with the Gulf of Maine and New England data. So we've been working to improve it by integrating training images from the 2022 bloom, as well as improving classifiers for other Arctic taxa. This has been a lot of back and forth, really iterative work, but I'm excited to report that at our latest assessment, our classifier is correctly identifying over 80% of the Alexandrium, so providing much more accurate information. As people in Alaska continue to build their own observing capacity, and if more IFCBs start to come to the region, we'll be able to share some of these classifier products, as well as all the other data that we've already collected to help people get up and running more quickly. I know Thomas Peruvia at Alaska Harmful Algal Bloom Network is already looking into purchasing an IFCB, and there may be others who are as well. So get in touch with us if you want to learn more about these classifier products or other ways that we use our instrument. I wanted to show some of the latest data coming from the IFCB. So as I mentioned, it's aboard Kevin Arrigo's cruise right now. They're watching how the ice algal community changes as the ice retreats. And so they're making a repeated loop offshore of Icy Cape and collecting some really incredible imagery. You can see this beautiful ice algal diatom community here, some Fragilareopsis, we've got some Thalassiosira, Coscinodiscus, no Alexandrium, so that's great news for everyone, at the moment at least. And it's actually been really cool for me. I'm a HAB scientist, so I'm always like looking through these images, just picking out the toxic cells. But it's been really awesome to have this opportunity to see all of these other incredibly productive and important phytoplankton that live in the region and that make this part of the world such a unique place. And so today I've obviously been focusing on the data and the results from our group here in Woods Hole, but I don't want to ignore all of the awesome things that are happening right there in Nome. Alaska Sea Grant and Norton Sound Health Corporation have secured their own event response funding from NOAA to do proactive outreach and education about harmful algal blooms this summer. I know that Emma's doing routine water testing and microscopy to look for harmful algal species. They're also working to build seafood testing capacity in the region. So there is already a lot being done to make sure that the Bering Strait region is more prepared for future blooms. So I want to close with this quote that I found when I was actually preparing this talk. This is from one of the scientists, Clarice Jensch, who responded to the first ever Gulf of Maine bloom back in 1972, so almost 40 years ago now. All of us, the medical professionals, the clammers, the public, the scientists, and knowledge seekers, were utterly surprised by the outbreak. There was so much we didn't know, from how to test to how best to keep the public safe. It took individual communities being willing to come together to share experiences and being willing to change for us to begin to find real answers. And I wanted to share this because it can be really alarming to have one of these harmful algal blooms right in your backyard. And what happened here last summer was really unexpected and alarming. But there was a time in the Gulf of Maine where this was a new and scary thing, and they've come a long way from that. Now, when blooms happen in New England, we have advance warning, we have managers and coastal stakeholders who are able to monitor, respond to, and mitigate the effects of these blooms, and most importantly, to protect public health and food security. So obviously, Alaska and the Bering Strait are a very different place in many, many aspects. And with these harmful algal blooms, it's never going to be a one-size-fits-all solution. But I do hope that this can be a hopeful note to end on. These kinds of events are big, but they're manageable. And from our group's perspective, we want to learn and share knowledge with you all so that you can decide what kinds of responses are going to be most appropriate for your region. And with that, yeah, thank you so much for sticking with me, for having me as a graduate student. It's just been such an incredible opportunity to work in such a unique and important place. And so I'm really glad to have had the chance to share a little bit of that today. And then, of course, thank you to all these folks and probably many more that I forgot to include, and also all these funding sources. So, yeah.
Awesome. Well, thank you very much, Evie. And before we start the questions, while you're thinking of your questions, this is the time we ask that the Straight Science audience, which is really good about this, the Straight Science audience give some love for Evie Fachon in the chat box, because it is never easy to be a public speaker. And she did a magnificent job. You already got, look at that, you already got a kudo right there. So it is, show her some love there from the Straight Science audience for letting us learn a lot more about harmful algal blooms and what happened here, and kind of where we are. It's amazing to me the technology that's available to have yourself sitting in a desk zoomed way over on the Atlantic Ocean, be able to see, I think real time, what the ship Sikuliak is swimming in, kind of plying the waters of, and what the algae is there. So it's very good. We learned big bloom, very toxic and scary, but that there's stuff being done. And I like the way you ended that with, it's a first for everybody. It was a first in New England when they noticed it. Southeast Alaska has to live with this every year, and how we move forward and get ourselves informed and take action will help us all. We have some other unique challenges, but with that, let's get to, we have several callers online, and they've been very patient because it's very difficult to be a caller on a Zoom call where you cannot see the slides. Maybe you can on your phone, I don't know. But I'm going to leave it open for if the callers at any time want to ask a question or speak their mind, just butt right in. I think the unmute is *6. And if you're having trouble unmuting, you can always text my cell phone, and that is 907-434-1149, and we'll be able to work through the cell phone and get your question to Evie and answered if for some reason you can't be heard. So callers, jump right in at any time. Just butt right in if I'm not paying attention. With that, we have one question in the chat, but it's direct to me. Can the but I'm going to say it because I don't know the answer to it, and you will probably, Evie. Can the IFCB, that's the automated imaging robot that's on board in that canister, can it go on an autonomous surface vessel or surf vessel? And maybe the U.S. Coast Guard Healy might be able to help out in that regard. And you also got a thanks for such a good update.
Oh, thanks. Yeah, that is a great question. And so the answer is yes, that's something that folks are working on. Mike Brosnahan, whose photo I showed in the beginning with our whole team, has been working to get an IFCB aboard an autonomous boat here in the Gulf of Maine. And that's been kind of just getting started, up and running, but it is working. And I think there are a lot of opportunities to utilize this kind of technology in an autonomous format. However, these are really expensive instruments. It's $130,000 just to get an IFCB in the first place. So anytime you're putting an instrument like that aboard an autonomous vessel, you need to think really hard about where you're funding it and how you'll be able to access it if it needs some attention. And so for that reason, it's really nice when we have it on a vessel or on some sort of shore-based platform where we can get to it really easily. But I think this technology is moving in a direction where more autonomous sampling is going to be happening, which is really exciting.
Terrific. Thank you very much, Evie. Rick Toman, you have your hand up. Go ahead.
Thanks very much, Evie. Great presentation. So I had a question, and you may not know the answer to this, but the current work of the Sikuliak, you showed some really cool pictures there at the end. It turns out, of course, that this year is an extremely high ice year by modern standards in the Chukchi Sea. Have we just gotten lucky at this? If it had been a more normal year, would we not have been able to do this work, or would have they just gone to where the ice is? Do you know that?
I think that is a good question. I know that Kevin Arrigo's focus is looking at these ice edge and under ice blooms. So I believe the plan for him was to always go up and work near the ice edge as far in as the Sikuliak can get. It's ice capable, but it's not an ice, like it's not an icebreaker breaker. It can't get in too far into multi-year ice, but it's doing the work that they had intended to do. I think if the ice had been further away, they just would have powered further out and made it to there.
Okay, great. Thank you.
Yeah.
All right. Any questions? Vicki Cornish with the U.S. Marine Mammal Commission. Hi, Vicki. Is there monitoring going on in the Gulf of Alaska or further south to see whether there are blooms there and whether they have the same characteristics?
Yes, yeah, there's a lot of work going on down in the Gulf of Alaska. I wish Julie Matweyu or maybe Steve Kibler was on this call, because they're really the ones who are doing a lot of that work down there, sampling shellfish and other organisms, as well as water sampling to look for the harmful algal species. But yeah, I know less about that region because all of our work has been focused up in the Bering and further north, although after looking at that new SIST map, it seems like we might need to be doing some more work down south. But there are a lot of folks who do have that region really well covered, especially since it has such a long history of paralytic shellfish poisoning down there. There's more of an established network and infrastructure for doing this kind of monitoring.
That get at the answer, Vicki, you're looking for?
Great.
Okay. And Megan Gannon with the Nome Nugget has her question, has her hand raised. Go ahead, Megan.
Thank you, Gay. And yeah, thank you so much, Evie, for the presentation. I know we're talking about HABs as an emerging threat, but I was wondering if you could tell us whether scientists have any tools to reconstruct blooms from the past, like in years where we might have not have a concerted monitoring effort. Are there any ways to look for these that might have happened, I don't know, before when we weren't looking for them?
Yeah, so a part of the reason that we collected cores this past summer was so that we could look at cyst distribution throughout different levels of the sediment and see if we could learn anything about past bloom events from those distributions. It gets a little challenging, especially working up in the Chukchi, because there's such a rich benthic community and there are so many worms and clams and all these other organisms that are churning up the mud and turning it up. So it's really hard to get like a nice signature in the cores that we can really definitively link to some time in the past, although we have isotope data from those cores and we'll continue to see what we can tease out from there. There are also some techniques for looking at ancient DNA in sediments and cores. So the cysts themselves, you might find them in the top of the core, but if you have a really long one that's several meters deep, as you get down there, further down, the cysts will start disappearing. And it's not necessarily that they weren't there, it's just that they can't survive and maintain their structure in the sediment for that long. But then we have other tools like ancient DNA that could potentially pick up the signature of those cysts. So that's not something we've done yet, but it's something we're looking into, and hopefully that could potentially be a way to look at this a little bit. Does that answer your question?
It does, yeah. Thank you so much.
And this is Gay. I would add that also in the Bering Strait region, I would say lack of data, Western science data, does not mean a lack of knowledge about what's happened in the past. Mm-hmm. And so we have tremendous untapped, honestly, database all around us in the Bering Strait, honestly, on both sides of the border. So this is a transboundary issue. And I think there's a lot to be learned by talking with and involving maybe and having a more formal project on what we already know. There's place names that indicate there was red tide and this may have happened in the past. You know, in the past around here can be quite far back in people's memories and stories. So, and data. So I think there is something also to be said, not just those cores, which go back, you know, tens and hundreds of thousands of years, but also what do we know in the region that's held in the collective knowledge of traditional knowledge. And I think that's something that's been untapped and needs to be, we could all learn from what everyone's experienced or knows about in this region. Thanks. That helps.
Absolutely. Thank you for bringing that up. That's huge.
And then my question, since no one's got their hand up yet, so I got a couple. One is that that's interesting. Where did the bloom come from? Because the Alaska coastal waters are not our richest waters, right? They're kind of, we get the Yukon River dumping in there, lots of heat, lots of sediment, lots of fresh water. And our side on coming up from the waters roll south to north, they're pretty, hit all the Kuskokwim River, Yukon River, they're kind of washed up a little bit and tapped out. But that was such a big bloom. I mean, toxic, persistent, large, like it was being fed like gasoline to a fire, sort of, if, in my mind. And so we know that the Gulf of Onadir, opposite Norton Sound, in the mirror image of the Bering Strait region to the west, that is rich, rich water. And, you know, the currents kind of come from the Gulf of Onadir in a northeasterly direction across St. Lawrence Island and on up. Is that because you're having trouble determining it because the ship had to stay only in, you guys had to physically remain in Alaska coastal waters, sort of, because you were on the US side? Is that part of the issue? If you were able to sample on both sides comprehensively, would you think you would have been able to target that bloom more precisely?
Yeah,
okay.
Absolutely. It's really too bad that our communication with colleagues and folks in Russia is so limited right now, and it needs to be for international reasons. But before some of the conflicts that have started in the past year, we did have a grant funded to be working with folks over in Russia and actually collecting data on both sides of the Strait and the Bering Sea and sharing information about cells in the water and cysts in the sediment to try and put together a better big picture of what's going on in the region, because you really can't, like, algae don't care if they're in Alaskan or Russian waters, they're going to go where they're going to go. And same thing for so many animals and other organisms that live in the region. So it's pretty hard to put together the full picture when you only have half the puzzle. But we do have some data from, like, we know sea surface temperatures on the other side. There's some other things we can get potentially from satellite imagery. So we have a few tools that we can try and work with to tease it out. It's just not the full set of tools that we would have in an ideal situation. Yeah.
Right. And that's a big issue for us in the Bering Strait region, with shared marine resources, with one shared water body or multiple water bodies that are mixing in our neighborhood with Chukotka. So for me, I don't know, there's some people on this call that may have some more East Coast contacts, but I would say, you know, if you're talking about the Bering Strait region, you would be thinking also about State Department, you know, getting at the science, or the Office of International Affairs for Department of Commerce or Department of Interior. I mean, I think there's things that at that level aren't tapped for this. And this involves human health and conservation issues with, pick your animals, but marine mammals, seabirds, you know, all that, but human health. And so for those listening that live in the region, know that Emma Pate and I, if we get a message from Sikuliaq, or if any of our seawater sampling efforts or any efforts in the Bering Strait region show that we have some danger or cause for concern, know that we will, thanks to some funding from the National Centers, NOAA's National Centers, now I'm going to butcher it, of Coastal Ocean Sciences, we will be putting, and we're going to start this week, just getting used, just a PSA for algae for the next Nome Nugget cycle. We've got advertisements. We will have space in the Nome Nugget, so we will be putting information there. You know, even if there's nothing to worry about, we'll put that in. And we will also be, if there's any kind of alarm signals coming in from any of these data points, we will be engaging the KNOM radio, KICY radio, And in both cases, we'll be trying to get the messaging translated into appropriate languages in our region, multiple. So in St. Lawrence Island, Yupik, and Bering Strait dialect of Inupiaq, as well as Russian, because that will be the way that we know the KICY, we know that goes pretty far over into Chukotka, and KNOM is picked up along the coast over there. So we will be notifying your relatives, friends, colleagues, neighbors across the way that we just are separated from right now. So know that locally, regionally, we will be, and if anyone has any other ideas on how to get that done, please let Emma Pate at Norton Sound Health Corporation, Office of Environmental Health, or myself know. We're trying to get it so that if something goes untowards, we will all be in the know, and including our neighbors, because this is something that is important. Dean Stockwell, thank you. Got your hand up. Go ahead.
Yeah, first of all, Evie, nice talk. Really enjoyed it. In regards to Dave's question, I don't think it's just East Coast and West Coast waters moving up into the Bering Sea. I think it's more complicated in that you have a lot of Gulf of Alaska water moving into the Bering Sea up along the shelf break, and it moves to the north until it hits one of the canyons, and there's a lot of upwelling that takes place. So that's a third source of cells coming up into that area. And if you go down to Sand Point right now, you're going to, in the Aleutians, you're seeing very high toxin levels from Alexandrium. That material is being moved into the Bering Sea and being moved north. And when Kevin Arrigo's cruise comes to the south and actually gets towards the Bering Sea, and with your system still running, I bet you start seeing more cells, because right now they're up towards the ice edge. Yeah. And yeah, they're going to see a lot of ice algae. But I think it's very complicated. I don't think a lot's coming up the Alaska coastal water, but if you look up what's moving along the Alaska shelf break in the Bering Sea, that's an avenue of cells. And I guarantee you, if you even go back to the 1600s, where they had a massive Alexandrium bloom in southeast, I bet those cells were going up into the Bering Sea. And, historically, you can probably get some of that material out of sediments. But again, as you said, it's very complicated. But again, great job tonight. Appreciate what you did.
Yeah, thanks, Dean. I've been spending a lot more time squinting at those current diagrams of the Bering Sea lately and thinking about, like what can be coming from more central or along the shelf break for sure. That seems like something that really needs to be considered. And in my presentation, I showed that model that we have for the Gulf of Maine, where they took the CIS data and the current data and other environmental parameters and actually modeled that bloom and how it progressed. And I think soon we're going to get to the point with Alaska where we actually have a lot of this really large scale CIS data and a lot of large scale environmental data. And I know Don and some of his colleagues are talking about trying to start putting together some of these large scale models where we can kind of experiment with the currents and different CIS sources to see how these blooms might grow and travel when they start in different locations. So that's another way to potentially get at what's happening on the other side of the Bering Sea. Since we can't go there ourselves, we can use models as a kind of tool to experiment and think about what might be happening.
So another quick question.
Yeah.
Yep.
Comparison with East Coast blooms. The data you showed primarily here was primarily surface. Once you go below 20 meters, your numbers dwindle. Is that the same thing on the East Coast?
I believe so, but I'm actually going to punt that one to Don if he's able to hop on, and because he's been really doing the East Coast and these Atlantic blooms for forever. Donnie there?
Sure. Yeah, I'll give a quick response there. Hi, Dean. It's really much the same. But the numbers are lower. We have more cells in the surface, the surface, and maybe down to 10 meters. Some occasionally when you get down to 20 meters, but and then you get below the mixed layer and they're gone. So they've got a surface manifestation, but typically in the open waters of the Gulf of Maine, if we see 5,000 cells per liter, that's a pretty high number. You get down further south in sort of more enclosed areas like Massachusetts Bay, we have seen 50,000 and maybe even 70,000 cells per liter. But to have an event like this one, where it was well over 150,000 and covering a large area, surface waters down a ways, this was much, much bigger than anything we've seen. And if you, Evie didn't talk about it, but these cells are a lot more toxic out in the Alaska region than the ones we have in the Gulf of Maine. We've got, with all of those different toxin profiles, the ones in Alaska that we've looked at, well, from this last bloom, had the most potent toxins in them, and the ones we get in the Gulf of Maine have some, but they're not nearly as toxic as that. So it was similar vertically, but much more abundant than anything we've seen in terms of cell numbers and in toxicity.
Yeah, thanks, Don. Really appreciate that. And give Evie a pat on the back. Great talk.
Yeah,
Give her that PhD.
That's right.
So quick, I know it's like 11:35 for you guys back east, but Don, is there a reason why we might be more toxic? Is that based on the nutrient high load in the Gulf of Onondaga water, or do they know why? What's the driver for toxicity for it to produce that high-end toxin?
Well, as an advisor, I'm going to let Evie answer that question.
Oh, okay. Sorry, Evie.
Because she can do it.
You're on.
Yeah, so I think that the toxin profiles that we see these cells producing are generally like genetically encoded. So it's not like the nutrients don't necessarily change the different like profile of the toxins. They might change it a little bit, and the nutrients might affect the total amount of toxin that it's producing. But overall, these profiles actually remain pretty consistent in different strains of these cells. I'm going to share my screen real quick. Let me see if I can find this slide.
And while you're looking, go ahead.
Yeah, so there have been other studies, the Japanese Natsuike, Gu et al., Orlova, who have taken sediments from different places around the region and grown up Alexandrium cultures from cysts that they isolate in those sediments. And these are some of the different profiles that they've seen from around the region. So we've got up here in the Chukchi, they isolated some strains that had really high levels of almost all saxitoxins. That's like super, super toxic. Down off the coast of Russia and around the Kamchatka current, we can see that there are some with like a lot of this GTX5. There's a couple that look like that. And so we're hoping to be able to use these toxin profiles a little bit like fingerprints to help us maybe deduce where these Alexandrium might have come from. The confounding thing with this is that the 2022 bloom and the 2019 bloom don't look anything like any of these other studies have found so far. So we don't really have that like smoking gun to point to tell us this is where it possibly started. And we've also, beyond this map here, I've established a bunch of cultures from cysts that we've collected in 2018 and 2019 to see what kind of toxin profiles we get from those. And those have all been really, really variable and different. So it's been a much more complicated story than we thought when we started doing some of this. Don, I don't know if you want to add anything there.
Well, just that, I mean, you're correct in answer to Gay's question, that nutrients can only affect that toxin fingerprint a little bit. You have to really stress the cells out before they change that profile. But it's I won't call it luck, but to determine why you had so much toxicity, there were some cysts that were very toxic that germinated, caused a bloom that the currents and the winds took up your way, and this year it was really a toxic one. In other years with other systems, you could imagine situations where, I mean, some of Evie's pie charts there were really weakly toxic cells. So you could have a bloom that originates somewhere else, but it makes it up into that region and isn't as much of a threat. So it's not the nutrient's going to help you get a big bloom, but it's not determining that fingerprint. The fingerprint is really just determined by where that inoculum actually started from, and that's obviously something we plan to go after.
All right. Well, thank you, Don. I have a question that's come in to me in the chat, again, directly, and it's for probably it's an oceanographic kind of question. So speaking of Gulf of Anadyr, there can be strong fronts related to that inflow into the Bering Strait. Is there any relation to strong fronts? These are often west coast of St. Lawrence Island.
Ooh, okay, that is a really good question. We haven't had the opportunity to look at fronts in that area, but we do know that fronts can be a place where bloom cells accumulate, particularly if it's like an upwelling front where you have like high nutrient water coming to the surface. There was a study that was just published this past year about some cells that were seen off the coast of Oceanographic in a frontal area. And so they studied the relationship of Alexandrium with the development of that front to show that the two were related. So I think looking in those Bering Sea fronts would be a really good avenue for future research in the region.
All right. And again, callers, we haven't had any caller. Feel free to Budinsky right in, because we can't get you otherwise. You just got to jump in, or you can text 434-1149 and I can get the question that way. iPhone, okay. Go ahead. Yep, go ahead.
Is this Gay?
Yep, go ahead.
Hey, this is Bivers.
Hi, Bivers.
Hey, I was on that Norseman 2 last month doing the biosampling or sampling with the walrus for a month of June. And I had talked with a young lady named Emily Bowers, and she was doing some sampling from the seabed to where I helped her. And, you know, she had this thing that goes down to the bottom and then collects the samples. And there was a lot of sand in that area where I think we were on Wainwright area. But prior to that, I was telling just about everybody on that boat that in our region, Norton Sound region, St. Lawrence Island, we have very strong currents out there. Diamete's got very strong currents, and our ice is really, it has depleted so much over time to where, to us subsistence hunters, it's not real ice we're looking for. But once we got up to Point Hope, I told everybody that was there, I said, I haven't seen this type of ice since the 70s and 80s. There was solid ice, really good ice. And we went up as far as close to 16 miles from Dukavik. We couldn't go any further. But my question is, since that the ice is not really thick nowadays compared to 70s, 80s, is there going to be more potential algae going up further? As a subsistence hunter, should I be concerned as to, you know, that's my backyard right there where I'm hunting subsistence with the marine mammals. Should I be concerned as a hunter?
Right. Yeah, that is a really good question. And I hope that, you know, Dawn, feel free to like jump in, and Gay, feel free to jump in after I take a crack at it. I'm glad you got the chance to meet Emily. We were working with her to help her get prepared for that cruise, and we'll be getting some of those sediment samples that you collected here in Woods Hole. So next time someone gives a talk, our new SysMap will have those included. But to get to your question, I think as the ice cover is for less of the year, it does give more of an opportunity to have these warmer bottom waters, to have this open water with lots of sunlight where the algae can potentially start blooming earlier or potentially stay later if the ice comes back later. So this is a process that is linked to a lot of things in the environment, and ice is definitely going to be one of them. It's not something that we think about here in New England because we don't have these seasonally ice-covered waters that you have, but it's something that needs to be considered a lot as we think about how these blooms will change and develop in the future. And as far as thinking about subsistence, I know there are a lot of folks working on trying to get better answers to that question. Kathy LaFay, who works at NOAA, has this EcoHab project looking at toxins throughout the food web, all the way from the plankton to the clams and worms, into walrus and bowheads and other subsistence resources. And so she's working, and others, Gay works really closely with her as well. There are a lot of folks who are working really hard to try and get better answers about where and how these toxins accumulate at different levels of the food web. So yeah, I know, Gay, do you want to add anything to that?
Sure, I'll try. You did a good job. So Bivers, the problem with all of this is Alexandrium. That's the type of this algae that produces this saxitoxin. It's one of, most algae in the ocean are just fine. The Alexandrium is not new to us, not new to the animals. It has been low level in our cold, ice-filled waters. It is not an algae that likes that likes cold water. So it blows up here and sets to the bottom and doesn't do much. Problem is, just like you notice, right? The ice is going because the ocean's gotten too warm. We're struggling with our ice. What happened last year was this Alexandrium, which likes warm water and which has never been able to make a good living that we're aware of in the past. I mean, in the most recent past, it got it's a plant, so it needs sunshine, it needs nutrients, it needs the right temperature, and it got the right temperature last summer. So what it did was it took off, and a bloom is when you have an uncontrollable growth. So you get these Alexandrium cells, boom, they split in half, whoops, and then those split in half, and all of those split in half, and pretty soon you have what's a bloom. It's sort of an uncontrollable growth event. Then the problem is, if you have a lot of Alexandrium in the water, it's got a lot of that toxin in the water, saxitoxin, with it, right? It's with it. And all the things that filter water for a living and eat algae, like krill, like upa, tunicates, like crab, clam, snails, then those are unaffected by the cold-blooded animals. Don't seem to be very affected by this nerve toxin called saxitoxin. So now the clam's healthy, looks good. The upa looks good. Everything looks good. Walrus comes along, eats 50 pounds of that. And each one of those little clams may have just that Alexandrium in it because we just had a bloom, a big growth of it. So that's all they're sucking up in their stomach. Then the clams, they got a big dose. That walrus eats 30 pounds, 50, whatever he eats. The clams are very toxic when his stomach starts to digest and crack, the stomach of the clam bursts open and now he's got lots of Alexandrium all at once in his stomach. That will affect the walrus. That will affect a human being. That will affect a seabird, marine seal, bowhead, whatever it is. And so anything warm-blooded. So yes, as a hunter, do you have a concern? Yes. Both from the health of animals, are they struggling? Are they eating and this stuff is what their food has been eating? Or for us, eating a clam right out of the stomach, without washing.
Yeah.
And that's a problem. The other thing that I lose sleep on a little bit, and that's why these researchers are coming into the area and we're trying to work with them, is when you look at the organs of a walrus or a bearded seal or some animal that's eating this, just like Evie had said, the animal or the human, you'll flush this out eventually if you don't get yourself in a pickle with too much of it, which can cause death. But if you can get help, they will just flush it right out of your body. So the transfer of the poison is happening through the intestine, the gastrointestinal tract. What are the organs flushing it out? The liver, the intestines. So there's work right now. That's some of the work that they're sampling suites of samples from a walrus during the hunt spring harvest at St. Lawrence Island, and I'll sample anything fresh. And they're looking at not just the unuk, the feces, to see what the walrus has eaten, but we really need to get at where is that poison? If it's in the animal, how much is in the liver? How much is in the kidney? How much is in the blubber? How much is in the meat? It looks like preliminarily, because we've been this project, EcoHab project, and I'm sorry I'm talking long, but I think this is important, that the muscle and the blubber of walrus, and maybe we don't know for the other animals, but you could use the walrus as a tester, that it takes too long for this poison to incorporate itself in the muscle in any meaningful manner, and in the blubber. So muscle and blubber, you don't even have to think twice of. For me, though, I think, what about liver, kidney, intestine? So we need lots of more data on that. We need to perhaps be testing, and there are ways to get the foods tested right now. So Norton Sound Health Corporation, Emma Pate, Office of Environmental Health, this office, me, we will test seafoods, and I will, through the Northwest Fisheries Science Center, we can get those marine mammal tissues sampled. So right now, this thing came upon us so unexpectedly. There's not a lot of data to draw on for walrus, any of the marine mammals, basically. There has been some done, just whether or not they have it and how much. That was something that was sort of a review. Evie showed that paper from 2016 that looked like, well, it's around. Walrus, maybe it's around a little bit too much, but that was 2016. 2021, boom, here we are with a full-blown, one of the most toxic, most persistent, most massive blooms of this warm water harmful algae species, and we're kind of trying to figure out where to get help, so, and where to start monitoring. So I hope that helps. Thanks for being patient.
Yes, everybody. Thank you. Exactly what you said, Gail or Gay. We do hunt for elders, families that cannot hunt anymore. That's another one of my concerns is giving this infected marine mammal to a family, which that's my concern, let alone us consuming it. And also, Evie, that was a great presentation, what you had done. And from what Emily said, I was told, or she directed me to Gay in regards to any algae bloom questions or concerns. So, and I told Emily that I've known Gay for years. So, and yeah, you are definitely the eyes and ears for our region here, Gay. I appreciate you as well, all the information you have given us. Thank you, Evie and Gabe.
Thank you.
Thank you, Bivers. There is a question in the chat box from Vicky Cornish again. Are there certain types of sediments that are more conducive to cyst settling?
Yes, definitely. I like that question. Cysts settle kind of like based on their size and density, like any other sediment. So areas that are really rocky and have high currents aren't a good spot for cysts to settle down, just because the currents will keep moving them right along until they get to a spot where they can settle. I'm sorry, it's getting late here, so I feel like I'm starting to get.
No, you're doing good. You're doing it. It's almost the midnight hour for you.
Let me share. I'm going to share my screen again, just because.
Hardcore, Evie, you're hardcore. Come on, it's good.
No, it is good. All right, let's see. So if we look back at our cyst map, we can see that we have this area up in the Chukchi with lots of cysts. We have this area down in the Bering with lots of cysts, but there's actually like not that much going on all around St. Lawrence or even in the Bering Strait. And that's not because blooms aren't happening here. We know that there was a huge bloom passing through this region this past summer, but the currents are just moving so quickly through here that it's not a good spot for the cysts to drop down and stay. And I think that any cysts that do settle down in the strait eventually get tossed up by currents or storms, and then just shuffled right along up into the Chukchi, where they have just a more calm environment that they can set down and stay. So yeah, I hope that's kind of a good answer. So yeah, sandy, rocky, pebbly environments, we don't see many cysts, but anywhere where the mud is really nice and fine, and we can tell that lots of fine particles are settling down, are generally the spots where we start to see them.
All right, thank you, Evie. Any other questions or chat comments? My last question is, and this isn't something you can really answer, I don't think, Evie, at all. So, but it's to everybody. And that is, I look at the map you showed with the cysts getting, you know, so the cyst is like that seed-like stage for this algae plant. And it's, yeah, we had trouble. We had trouble last year, and who knows, we probably will have it again. But the thing is, it all, you were saying those seeds are sitting in the northern Chukchi Sea. And I oftentimes think of our neighbors to the north. You know, we're going through this now. We're learning lots of things. We're trying to help when the Northwest Arctic Bureau had it kind of in Kotzebue Sound, right? They could draw upon what Norton Sound Health Corporation and the Department of Public Health were doing for Manilik to help their clinics and their people. And in general, you know, we're dealing with this right now, but I kind of wonder how we can best help, how the Bering Strait region, what we're learning, what we're doing. We really need to think about our neighbors to the north, as well as I think about our neighbors to the west all the time, because we're in the middle of this thing, or we were, and we were trying to figure out how to keep everyone safe and understand what the problems are. But I look at that as like a little bit of a big, I don't want to say ticking time bomb, but I guess I will, for as the warm water goes into that area in the northern Chukchi, you know, I look forward, I guess, to hopefully talking more to our neighbors to the north coastally, and making sure what we're learning down here, we can help others along the coast on either side as this gets to be something we have to deal with more, kind of like the people of Southeast Alaska, which do deal with this every year. So anyway, thanks, Evie. Thank you very much. Any other questions or comments in the chat? If not, we'll say, Evie, you are at the stroke of midnight. You are free of duty, and I hope your boss lets you come in a little late tomorrow to work. So fully understanding your go get them tonight and talking to us at midnight your time. So thank you so much. Excellent presentation. Emma's got a clap for you. Okay. There's all kinds of things going on here. So with that, I will say thank you to everybody who came on. Next time we're having Straight Science, and the reason we're slowing down on Straight Science is because we're doing some travel and dealing with a lot of outreach and education to deal with this particular topic. So stay tuned, safe and be safe, Bering Strait region. The next Straight Science will be, I think it's August 22nd. And I better call it up because mine's late for me too. And we're going to have NOAA's race division. So they are going to be talking about their Pacific cod tagging project, some of the results of that, and a project that they're going to be doing this summer at Savunga, I think, out of Savunga. So that'll be on August 22nd at 6:30. We'll have Pacific cod tagging project for the Northern Bering Sea, Bering Strait region out of St. Lawrence Island. So with that, Evie, Don, I don't know, Don, if he's still awake, stay on the line, but thank you so much all for coming, and we'll see you next time. Have a good night, everyone. Be safe, Bering Strait.
Thank you.